Let me tell you a story you'll probably recognize. You join a project, you open the code base, and you see a beautiful inheritance hierarchy. A base class, 5 subclasses, clean names, very object-oriented. At first, it feels elegant. Reuse everywhere, no duplication. Then one day, you change a method in the base class, and suddenly 3 unrelated features break. No compiler error, no obvious warning, just chaos. Inheritance doesn't usually fail immediately. It fails quietly. So today we're asking a dangerous question. Is inheritance a powerful tool or a design trap? Before we call inheritance a trap, we need to understand why it exists at all. Inheritance exists for a good reason. Formally, inheritance is when one class represents a more specific version of another and can share behavior. It's meant to model meaning, not just share code. When we say one class extends another, we're saying this thing is that thing. A credit card payment is a payment method. A savings account is an account. Inheritance lets us say all accounts share some meaning and savings accounts add more. When this relationship is real and stable, inheritance works beautifully. The problem isn't inheritance itself. The problem is why we reach for it. There's an important distinction most people miss. Inheritance can mean 2 very different things: inheriting a contract or inheriting an implementation. Inheriting a contract says, I promise to behave like this. In this case, a class isn't borrowing code. It's making a promise. There's no shared state. There's no shared algorithm, just a shared expectation. This is still inheritance, even though no code is shared. Inheriting implementation says, I'll reuse whatever code happens to be here. Here, the structure looks similar, but the meaning is very different. State flows down, logic flows down, and assumptions flow down with it. Almost every inheritance horror story starts with inheriting implementation, not meaning. When we say inheritance shares behavior, that can mean shared code, but it doesn't have to. This is what good inheritance actually looks like. Here's inheritance done right. The system doesn't care how a payment happens. It only cares that a payment method can authorize, capture, and refund. Credit cards, PayPal, bank transfers, all of them are payment methods. No shared state, no shared algorithm, just a shared promise. This is inheritance without inherited code. Here's the rule that decides whether inheritance helps you or hurts you. Is a relationship versus has a relationship. Is a relationship is about identity, what something is. And that identity has to remain true over time. Has a relationship is about composition, what something uses. A payment processor uses a fraud checker. It is not a fraud checker. The mistake happens when we say, I'll extend this class because it already does what I need. That's not modeling reality. That's borrowing implementation. And once you inherit implementation instead of meaning, you inherit problems you didn't ask for. This is the moment inheritance seduces you. You see a class that already logs, already retries, already validates. And you think, if I extend this, I get all that for free. It feels efficient. It feels clean. But what you're really doing is saying, my new feature now depends on every decision this class has ever made. That's not reuse. That's coupling. What you're looking at here is a classic pattern. It's called the template method. The base class defines the algorithm, and subclasses can customize specific steps. That means clear extension points and very few overridable methods. Most fragile base classes aren't broken by bad subclasses. They're broken because subclasses rely on assumptions the base class never promised. Let's make this concrete. You have a base class called payment processor. Credit cards extend it. PayPal extends it. Everything works. 6 months later, a new requirement arrives: fraud checks. Nothing here looks wrong, and that's what makes it dangerous. Seems reasonable. Credit cards pass. PayPal silently fails in production. Why? Because PayPal required user redirection before charging, an assumption about order the base class never declared. That assumption lived in the subclass, but the base class didn't know that. This is the fragile base class problem. Subclasses don't just depend on what the base class promises. They depend on how it's implemented. That dependency is invisible. A small change at the top ripples everywhere below. You don't know who depends on what. You don't know which override assumes old behavior. The deeper the inheritance tree, the higher the cost of change. In practice, this leads to a simple rule. One level of inheritance is usually fine. 2 levels should already make you uneasy. In business logic, 3 levels is almost always a design smell. Deep inheritance trees don't scale. They hide dependencies instead of managing them. Inheritance couples classes across time. Your future self pays for today's convenience. So is inheritance ever safe? Yes, when the base class enforces invariance, not workflows. Notice what's missing here. No workflow, no sequence, no assumptions about order. This works because the base class is small, stable, and opinionated only about rules. It doesn't try to control how payments happen, only what must always be true. This is the other kind of base class. It doesn't control the algorithm. It protects the rules. The base class protects rules, not behavior sequences. This kind of inheritance works because it reinforces encapsulation instead of fighting it. Now look at this. On the left, we have a workflow-driven base class. The base class controls the sequence. It decides the order of steps. It owns the algorithm. That makes it powerful and fragile, because every subclass is forced to align with an implicit flow. And any change to that flow silently redefines the contract. That's the dangerous kind of inheritance. On the right, we have something very different. An invariant-driven base class. No workflow. No sequence. No assumptions about order. The base class doesn't tell subclasses how to do things. It only enforces what must always be true. Rules, not steps. That's why this kind of base class is small, stable, and safe to inherit from. It doesn't control the algorithm, it protects the rules. The base class protects rules, not behavior sequences. And that's why this kind of inheritance works. It reinforces encapsulation instead of fighting it. Now let's make explicit what we've already learned. Inheritance works, but only when three things are true. 1. The is-a relationship is unquestionable. 2. The base class is stable and rarely changes. 3. Subclasses don't override or reinterpret core behavior. Adding behavior is usually safe. Replacing behavior is dangerous. The moment a subclass has to override a method just to stay correct, inheritance is already failing. Let's make that last point concrete. In this example, the base class defines what a card payment is. It validates the card, captures funds, and says that authorization exists. Visa, MasterCard, and Amex only add behavior. They each authorize in a different way. Nothing in the base class becomes wrong. The meaning stays the same. That's safe inheritance. But the moment one subclass has to say, I need to skip validation, or I need to change how capture works, or I need to override this just to be correct, inheritance is already failing. At that point, the subclass isn't specializing the abstraction. It's fixing it. Adding behavior is safe. Replacing behavior is the warning sign. These aren't identities. They're capabilities. And capabilities don't belong in inheritance trees. This is why experienced engineers lean toward composition. Instead of inheriting behavior, we compose it. The service doesn't become a payment provider. It uses one. Checkout service owns the workflow. Payment provider handles charging. Fraud checker handles fraud. Logger handles logging. Dependencies are explicit. Blast radius is limited. Change becomes safer. Inheritance couples identity forever. Composition couples capability by choice. And capability is far easier to evolve. Composition isn't free. It adds more objects, more wiring, more explicit dependencies. But that cost is visible. Inheritance hides its coupling. Composition makes coupling obvious, and obvious problems are easier to fix. That doesn't mean compose everything. It means prefer clarity over cleverness. Here's the mindset shift that changes everything. Inheritance is not about reuse. Inheritance is a promise. When you extend a class, you're saying, anywhere this base class is expected, my subclass can safely replace it. That idea has a formal name: the Liskov substitution principle. If replacing the parent with the child breaks the program, the promise is broken, and inheritance was the wrong tool. Every overridden method quietly rewrites part of that promise. That's why inheritance demands discipline. So let's wrap this up. Inheritance is powerful, and power amplifies mistakes. Use it only when the is-a relationship is real. Avoid it when you just want reuse. Be cautious of fragile base classes. And remember, composition is often safer. Inheritance alone isn't what makes object-oriented programming shine. The real magic happens when behavior changes without changing the code that depends on it. That's polymorphism. Behavior changing through shared contracts, and that's what we'll talk about next. One last clarification. Polymorphism does not require inheritance. It comes from shared contracts, not shared code. Inheritance is just one way to achieve polymorphism, and often not the best one. If you've ever been scared to refactor, now you know why. I'll see you in the next video.